And welcome. So we heard from Sir John Armitt, Chair of the NIC, this morning about the Commission's vision for the UK's roads, including how we prepare for the growth of electric and autonomous vehicles. We're pleased to hear now from the two winning entries from the Commission's recent Roads for the Future competition. Unfortunately, Sir John is not able to introduce them both, but the jury chair, Commissioner Bridget Roswell, has provided the following perspective. From the 81 entries, the jury chose two from Leeds City Council and City Science of Exeter. Leeds' proposal shows how we can harness enhanced traffic data to prevent tailbacks, while City Sciences sets out a process for gradually integrating driverless cars and buses in our city centres. Both winning entrants demonstrated creativity and ingenuity. This is just the beginning of getting our road system ready for the cars of the future, and these winning ideas are a great starting point for a wider debate that looks beyond the vehicle itself and towards the roads they will travel on. The Commission hopes the competition will encourage further innovations that consider both how these vehicles will be driverless and how they could be connected using the latest digital technology. And first off, we're going to hear from Joel Dodsworth from Leeds City Council.
Yeah, I'm Joel Dodsworth, Youth MC Manager at Leeds City Council, and basically that means I'm in charge of traffic signals and how they operate. So our proposal, slightly biased, but was about traffic signals and how we could make those CAV ready. So that's me, not the owl. So yeah. Just to give a little bit of background, I suppose, to traffic signal control, for those who aren't aware. Fixed time UTC. So a lot of in fact in Leeds, but in a lot of cities where you've got dense networks of signals, it's still pretty common to run fixed time plans, and they can get updated every year if you've got a lot of resource, or they can be 10, 20 years old. And there's a degradation in performance associated with that if you don't keep up to date with those plans. Slightly more sophisticated, System D VA, so that's vehicle actuation. That's really common across the UK still at sites that tend to be junctions that tend to be kind of fairly isolated junctions. And basically, the premise of that is that whenever a vehicle is present, you carry on extending a green signal, and then you reach some pre-specified point, and you say, right, that's the maximum. We're going to move on. It's not really truly optimizing, but it's better than nothing. And then in the 80s, 1980s, that is, Mover came along, which is TRL, we've got a stand over there somewhere, developed that. And Mover is a little bit more sophisticated, so that's actually judging the intensity of traffic that's arriving at the junction and making decisions on when to change stage, serve different arms of the junction. So that's the background. So the constraints of so what we're looking at in this proposal is about the way that we detect vehicles for the optimization strategy to work. So just to go through some constraints of conventional detection. So these optimization strategies such as Mover and Scoot, which are the kind of considered the state-of-the-art control strategies in the UK, they both have an optimization model. It's an online model, not connected to the internet, but as in it's real time. It's a live model representation of the traffic conditions at the junction. Now, conventional detection, and by that I mean inductive loop detection, so just a loop cutting the road, for those who don't know. You get a 1 or a 0. So if there's a vehicle on this loop, you get a 1. If there isn't, you get a 0. And from that information, we have to build up a model of what's actually going on at a junction. So in some ways, that's quite limited data. It's quite reliable data, but it's quite limited in what we're receiving. Speed of the vehicle arriving is unknown. And the vehicle positions, so you have a detector, it might be 100 meters upstream of the junction. Beyond that, the position of vehicles is just an estimation. So you can see that there's there's plenty of room for error, basically, in the way that the optimizer works. So this is just an example. So you've got down at this end your inductive loop detector buried in the road, say 100 meters upstream. Beyond that, you've got to estimate everything, queue length, position of the vehicles, and so you can end up with an error in the actual position of a vehicle compared to the model position. And if you've got error in the model, then the optimizer's not making the best decision that it could. So that's the kind of current situation. So our proposal was to say, well, what we want to do is to make our infrastructure CAV ready, so connected and autonomous vehicles, obviously. We want to make it ready for the sort of data that we would expect to receive from those vehicles. So that is things like the position of the vehicle, the speed of the vehicle, maybe the type of the vehicle. That data isn't available yet, enough of it for us to actually develop our systems and have a business case for doing that. So our proposal was to actually use existing technology, but in a different way from how it's being used at the moment. So radar detection is used in the traffic signal industry a lot, but it's used to basically do the same job as conventional detection. So that's still saying, if there's a vehicle there, you get a 1. If it's not, it's a 0. So we're using it slightly differently, and I'll go on to that. So this allows us to kind of mimic what we would expect to receive from CAV data, which allows us then to develop our systems to be able to accommodate it. So this is an example. So you have a radar detector that's basically mounted on top of your traffic signal pole. And rather than just giving us, like I say, a 1 or a 0, are the vehicles present or not, we're actually tracking the vehicles through the junction. So every half a second, say, we're saying, this is the distance of the vehicle from the stop line, this is the speed of the vehicle. And that allows us to make much better predictions of when those vehicles are going to arrive at the stop line. And so the optimizer can make better decisions. So eventually, we had envisaged that you wouldn't need the inductive loop detector or equivalent anymore. So as I said, this is a kind of a proxy for CAV information. And it allows us to break down the barrier that we've got at the moment, which is that for us to develop our infrastructure for CAV data, we need some CAV data to do it, otherwise we don't have a business case to do that. And likewise for vehicle manufacturers, what's the point of them equipping their vehicles with the relevant technology to give us that information if we can't make any use of it? So this is allowing us to kind of break that cycle and get on with developing our side of things. So one of the advantages of this is that it's less resource intensive than the current way that we do it. At the moment, when you implement something like Mover with conventional detection, you have to have an engineer go out and they spend 1, 2, 3 days validating all of the model parameters. Things like speed that we don't know, they have to enter an average speed. And there's various other things. So what this does is actually it vastly reduces the amount of engineer time that's required. And it means that the revalidation of these parameters that has to occur every few years doesn't need doing, because things like speed and position, they're just constantly being updated. There's some wider benefits of this proposal, which is actually the detectors, while they're doing the primary use case of what we want the data for, actually it's also providing us lane-specific speed data. It's a source of continuous data collection, so certainly with the video detection stuff that we used, you could be pulling out live turning counts at a junction 24 hours a day, 365 days a year, rather than having to send out a survey company for a 12-hour spot count one day that's not necessarily giving you a full picture of what's going on the network. And the other thing is that it allows us to do some incident detection, so where you're looking at the flow and the speeds, and you can actually start to say, well, actually, if that drop in speed is something that we wouldn't expect at this time, then that may be an incident. So it allows you to automate some of that. This is just a screenshot from our trial site that we set up. So there's a webcam that was just mounted next to it. But this is actually radar detection, which is AGDs, for anyone who's interested. So you can see like the distance is on the cone. And I don't think I can play it, unfortunately. It'll have to just be a screenshot. But what you see is the vehicles tracking towards on the camera, and you can see those tracks on the actual radar, which is showing us the speed of those vehicles as they come through the junction and the distance, which is exactly the sort of information that we're looking for. So it's a successful trial. And the next step, so what we're actually doing now is building on this, and obviously you saw on this trial it's just a single camera or a single radar detector. We're going up to a full junction trial, and we have a system in Leeds that we're fortunate to have called Spruce, which was developed quite a long time ago, and in some ways is a bit old hat, but it's a development environment, and it actually allows us to develop a control strategy that deals with this type of data, so we can actually get a proof of concept up and running quite quickly. So that's what we're actually on with now, and obviously joint winning this competition has been really helpful for us to give a boost to that. Some of the other things that we'd really like to do with this, once we get it up and running properly, is to actually publish the data that we're pulling from these units and make it an open data source for whoever wants to get hold of it. That's me done. That's the end.